Black holes are not eternal. They radiate. They shrink. And given enough time, they explode. The mechanism that kills them operates at the boundary between quantum mechanics and general relativity, in a place where neither theory works alone. In 1974, Stephen Hawking performed a calculation that shocked the physics community. He showed that the event horizon of a black hole is not perfectly black. It glows. Faintly, imperceptibly, but it glows. And that faint glow carries energy away from the black hole, particle by particle, photon by photon, until nothing remains. To understand how this happens, consider empty space. In quantum field theory, the vacuum is not empty. It is a seething ocean of energy fluctuations. Pairs of virtual particles pop into existence and annihilate each other continuously. This happens everywhere, all the time, in every cubic centimeter of the universe. The vacuum is not a passive background. It is an active, restless medium, constantly borrowing energy from the future and repaying it an instant later. Physicists call this the zero-point energy of spacetime. Even at absolute zero temperature, with all heat stripped away, quantum fields still vibrate. They cannot be completely still. The Heisenberg uncertainty principle forbids it. Energy and time are linked in such a way that the more precisely you fix one, the more the other fluctuates. Normally, these pairs are born together and die together in a fraction of a second. Their net effect on the universe is zero. But at the event horizon of a black hole, something extraordinary occurs. Imagine a virtual pair that appears right at the boundary. One particle materializes just outside the horizon. The other materializes just inside. The particle inside is immediately trapped. It cannot escape. It falls toward the singularity. But its partner, the one born just outside, suddenly has no one to annihilate with. This orphan particle escapes into space as real radiation. It carries real energy. And that energy has to come from somewhere. It comes from the black hole itself. The mass of the black hole decreases by exactly the amount of energy carried away by the escaping particle. This is Hawking radiation. A quantum mechanical process that slowly, relentlessly drains a black hole of its mass. There is a deeper way to see this. An observer hovering just outside a black hole, using rockets to maintain their position against the pull of gravity, is not in freefall. They are accelerating. And here, a remarkable phenomenon discovered by physicist William Unruh becomes relevant. An accelerating observer does not see the quantum vacuum as empty. They see it as filled with a warm bath of thermal radiation. The stronger the acceleration, the higher the temperature of this radiation bath. At the event horizon of a black hole, where the required acceleration to hover becomes infinite, this Unruh temperature becomes the Hawking temperature itself. The two effects are the same phenomenon viewed from different reference frames. This is one of the most beautiful unifications in all of theoretical physics. The temperature of this radiation is inversely proportional to the mass of the black hole. The exact formula, derived by Hawking, contains the gravitational constant, the speed of light, Planck's constant, and Boltzmann's constant, all bound together in one equation. A stellar mass black hole, roughly 10 times the mass of the Sun, has a temperature of approximately 60 millikelvins. This is colder than the cosmic microwave background radiation that fills the universe. So cold that the black hole actually absorbs more energy from its surroundings than it emits. This means that right now, every black hole in the universe is growing, not shrinking. The cosmic background radiation feeds them faster than Hawking radiation drains them. But the universe is expanding. The background radiation is cooling. In roughly 10 to the power of 14 years, the cosmic microwave background will become colder than the smallest stellar black holes. At that moment, evaporation begins in earnest. This mechanism was first proposed by Stephen Hawking, and has since been explored through stunning visualizations by science communication channels. The mathematics describes a black body spectrum, identical to the radiation emitted by a hot coal. Every object with temperature radiates, and black holes are no exception. As the black hole loses mass, its temperature rises. And as its temperature rises, it radiates faster. This creates a runaway feedback loop. The smaller the black hole gets, the hotter it burns, and the faster it shrinks. A black hole with 10 solar masses will take approximately 10 to the power of 67 years to fully evaporate. This is a number so large that the current age of the universe, 14 billion years, is essentially zero by comparison. 10 to the power of 67 is larger than the number of atoms in every star in every galaxy in the observable universe, multiplied by itself. But time is patient. And eventually, the black hole shrinks to the mass of a mountain, then an asteroid, then a building. At this stage, the temperature is billions of degrees. The radiation output is enormous. The black hole is no longer a dark, invisible predator. It is a blinding point of light, radiating harder and harder. In the final second of its life, the black hole releases its remaining energy in a catastrophic burst. The equivalent of millions of nuclear weapons detonating simultaneously. A flash of gamma rays, neutrinos, and elementary particles erupting from a point smaller than a proton. And then silence. The black hole is gone. The spacetime it once warped relaxes back to flatness. The event horizon dissolves. The singularity vanishes. Nothing remains but a fading cloud of radiation expanding into the void. But this death raises a terrifying question. During its lifetime, the black hole consumed stars, planets, gas, light, and information. Everything that fell in carried data about its quantum state. Its position, its momentum, its spin, its charge. Where did all that information go? If the black hole evaporated into perfectly thermal radiation, then the radiation carries no information about what fell in. It is random noise. Featureless. This would mean the information was destroyed. And in quantum mechanics, information cannot be destroyed. Ever. This is a fundamental law, as sacred as energy conservation. This is the black hole information paradox. One of the deepest unsolved problems in theoretical physics. Hawking believed the information was lost. Most physicists today believe it somehow escapes, encoded in subtle correlations within the radiation. But the exact mechanism remains unknown. In 2013, a group of physicists proposed something even more troubling. They argued that if information is to escape, the particles of Hawking radiation late in the black hole's life must be entangled with the particles emitted early in its life. But the particles falling into the black hole are also entangled with their partners inside. This double entanglement, called monogamy of entanglement, is forbidden by quantum mechanics. Something has to give. Their conclusion was that the event horizon cannot be a smooth, invisible surface. It must be a wall of energetic radiation, a firewall, that would destroy any infalling observer on contact. The peaceful crossing that general relativity predicts would be an illusion. This proposal split the physics community. It cannot be reconciled with general relativity, which insists freefall through the horizon is uneventful. Something in our understanding is broken. In 2019, a different approach emerged. A team calculated the entropy of Hawking radiation using a new technique borrowed from the mathematics of quantum gravity. They found what is called the Page curve. Don Page, a former student of Hawking, had predicted in 1993 that if information is preserved, the entropy of the radiation should first rise, then fall back to zero as the black hole finishes evaporating. For decades, no one could derive this curve from first principles. The new calculation produced exactly the Page curve. But it required a strange new ingredient. The calculation revealed that the interior of the black hole contributes to the entropy of the radiation through what are called quantum gravity islands. Regions of spacetime that, according to the island's formula, must be counted as part of the exterior when computing entanglement entropy. The mathematics works. The information is preserved. But the mechanism it implies challenges every intuition about where things are and what information belongs to whom. Hawking radiation means black holes have temperature. If they have temperature, they have entropy. The Bekenstein-Hawking entropy formula says the entropy of a black hole is proportional to the area of its event horizon, not its volume. This is a profoundly strange result. It suggests that all the information about what fell in is stored not in the three-dimensional interior, but on the two-dimensional surface. Like a photograph that encodes depth without actually containing it. This idea, that three-dimensional physics can be fully described by a lower-dimensional boundary, became the foundation of the holographic principle. And the holographic principle eventually gave rise to one of the most powerful tools in modern theoretical physics. A framework that connected black holes, string theory, and quantum field theory into a single consistent picture. A framework that rewrote our understanding of what space, time, and information actually are. Hawking radiation means black holes have temperature. If they have temperature, they have entropy. And if they have entropy, then an enormous amount of information is being destroyed. Unless it isn't. The answer to that unless is the frontier of physics. And that frontier begins exactly here.